Dear students, welcome to EPG Pathshala. This module is titled T-distribution and tests of significance based on T-distribution. We have seen in one of our previous module on confidence interval how to use the T-distribution to calculate the confidence interval of the mean. The formula we used is that the T, the constant T from the T-distribution multiplied by the standard error of the mean. The constant T is produced by this is actually made by a simulated data set where the exact population mean and the sample mean is known of the null hypothesis, in which the formula used is that the sample mean minus population mean divided by standard error of the mean. So in that way you can calculate a number of T, that is the T ratios, and you can plot that as a probability histogram. So that way you are going to get the T distribution. So you can use the T distribution for various tests. We have seen that how to use that for the confidence interval of the mean, and a number of confidence interval for the parametric method we use the T distribution. The other main test for the T distribution is students t-test. So that is used to compare the means of two groups, either dependent group or independent group. T distribution is also used for regression analysis and Bayesian analysis that we will come across in later modules. So today we will see how the T distribution is important and how the T distribution is used to calculate the t-test, which is very important test for the statistical hypothesis testing. So coming to it, the T distribution or the student's T distribution is a type of continuous probability distribution with exact probabilities of every T scores known. This enables us to calculate the p-value from a given T score. The T ratios plotted as in a probability histogram is called the T distribution. The shape of T distribution depends only on the degree of freedom df. With small degree of freedom, distribution is fat-tailed or platykurtic, while with the large values of degree of freedom, distribution become almost indistinguishable from the normal Gaussian distribution with thin tails. As you can see in this particular diagram, as the mu, that is the degree of freedom, increases, the distribution shape is almost like a bell shape or a Gaussian distribution. But if the degree of freedom, the mu, is 1 or 2, it becomes platykurtic, that is actually fat-tailed distribution. The history of T distribution is that it is developed by W.S. Gossett, who was working in Guinness Brewery, Dublin, Ireland then. To maintain the trade secret, Gossett published it in the pen name of student, hence the name of the distribution. There are many tests of significance based on the T distribution, especially the students' t-tests. To calculate the confidence interval of the means and difference between two groups means in linear regression analysis, in Bayesian analysis. So now let us see how t-tests and for the comparison of the means of the two groups can be performed. There are two types of groups. One is called independent group. For example, marks that the students get in one subject and another subject, which is totally independent. Disease incidence, temperature, all these are independent groups, while paired group is especially for the before and after study. For example, before a drug is administered and then after the drug is administered, or the students' performance in the first semester and the same students' performance in the second semester. So, or the left eye versus right eye, these are all paired measurements. There are a set of assumptions that the t-test does. So first assumption is that the samples needs to be random. Second is that independent observations or measurements. Third, accurate data. Fourth, populations with approximate Gaussian distributions. Beware that here the samples need not be the Gaussian. The assumption is about the population from which the samples came from. The fifth one is variance or the standard deviations of the two groups are nearly equal. This assumption is also known as homoscedasticity. The variance or the standard deviation has to be almost equal. So for the students' t-test, the assumptions are the subjects are randomly assigned to one of the two groups. The distribution of the means of the group is normal with equal variance or unequal variance. This defines two types of t-test in the Excel have. So Excel have got two types of t-test. T-test assuming equal variance and t-test assuming unequal variance. So to decide which one, we have to first find out is the variances are equal or unequal by f-test. Now the third one is the sample sizes between the two groups do not have to be equal. So sample sizes can vary, but the variance have to be approximately equal. Hypothesis of the t-test is that null hypothesis is that the group means are same, while alternate hypothesis is that group means are not same. It's nothing to do with the directionality. Not same means that either group 1 is higher than group 2 or group 2 is higher than group 1. So this is basically a two-tailed test. Comparing means of the two independent variable. Before the t-test, we have to check the distribution is normal or not normal. We can approximately do that by drawing a histogram or looking at the kurtosis and skewness. And if you want to be more rigorous and more formal, you can do omnibus K2 normality test. If normally distributed, proceed to the independent t-test. So if the distribution is not normal, you have to perform Mann-Whitney U-test or Wilcoxon signed rank test. Both are a non-parametric test, and of course it's not available in Microsoft Excel, but you can use a software like GraphPad Prism for this. Coming to F-test. F-test measures the equality of variance or homoscedasticity, identical variances between the two groups. Identical means approximately similar variances, not significantly deviating from the null hypothesis of equality. So that means that the variance can be different till a critical limit. There is a tolerance limit for that. So it doesn't mean that variance have to be exactly same. To do the F-test, first we have to calculate the F ratio, which is standard deviation of the group 1 divided by standard deviation of group 2 squared, where S1 is the standard deviation of group 1 and S2 is standard deviation of the group 2. So in this example, we are comparing old and young rats for certain measurement. So you can see that group on the left side is old, while the column on the right side is the young rats. So the statistics, the mean, as you can see, 30.17 and 53.71, with the sample standard deviation is written, standard error of the mean and sample size is there, from which we can calculate the F ratio S1 by S2 whole square, that is 16.09 divided by 10.36 whole square, that is 2.41. Now we have to decide what the degree of freedom for this ratio. So there will be two degree of freedom, one for the numerator and the other for the denominator. So dfn and dfd both will be respective group size minus 1. So degree of freedom for the numerator is 8 because its the group size is 9 minus 1 is 8. Degree of freedom for the denominator is 7 because it is 8 minus 1. 8 is a size, so minus 1 is 7. 8 minus 1 is 7. So from these three numbers, so three numbers means a degree of freedom numerator, a degree of freedom denominator, and the significance level, which is normally is 0.05. One can calculate the p-value. We can also calculate the critical p-value by using the F distribution table. So remember here the p-value is nothing but the F ratio. So we are comparing the F ratio with the critical value of that F ratio. So as you can see in this figure, we can actually see that 8 is the degree of freedom and 7 is the degree of freedom for the denominator. So we can see that the critical value of the F is 3.72. So the critical value of the table value, which is critical F, is higher than our obtained F ratio, which is 2.41. We can conclude that the P should be higher than 0.05 and our variances are not significantly different. So variances are almost equal. That is what the conclusion is. So whenever we are looking at T or F or chi-square table, remember that if the table value is higher than the obtained value, P must be higher than 0.05 and conclude non-significant. If the table value is less than the test value, P must be less than 0.05. A more accurate method calculate the exact P value of the F test. In our earlier example, P is equal to 0.2631, which is indeed higher than 0.05. Variances are not significantly different. So how to perform the t-test or how the t-test works? So first it calculates the standard error of the difference between the two group means. Similar to our confidence interval, I have already discussed that in an earlier module. In the case of confidence interval, we are multiplying a t constant with standard error of the mean. Here standard error of the difference between the two group means. So standard error of the difference between the two group means, the formula used is the whole root S1 square divided by N1 plus S2 square divided by N2, where S1 is the standard deviation of the group 1, N1 is of course its group size, S2 is the standard deviation of group 2, N2 is its size. For calculating 95% CI of difference between two means, the standard error of the difference is multiplied with a constant from the t distribution, or 1.96 is approximate. So the real constant, if you check out in the t distribution table, is 2.1314. So you multiply this value with the standard error of the difference is, that is 6.67, to get 14.22. So observed difference between the two group means is 53.71, that is the mean of the first group, minus 30.17, that is the mean of the second group. So the difference in the mean of these two groups is 23.55. If you express that with 95% CI, that extends in the both directions. So 23.55 minus 14.22 and 23.55 plus 14.22, which will be 9.33 to 37.76. Now the question is that, does this confidence interval include our null hypothesis? Our null hypothesis is that the two group means are same. So this particular range do not include that null hypothesis. Is that the group means of same means that group 1 mean minus group 2 means is 0. So the difference between two group means is 0. So here this particular range do not include our null hypothesis. So we can conclude instantly that the results are statistically significant and the p-value must be less than 0.05. So the width of the CI depends upon the variability. So low standard deviation or consistent data would lead to a narrower CI. Sample size large n would lead to a narrower CI. Degree of confidence, that is the confidence level, lower the confidence would lead to the narrower CI. It's the same thing as the standard error of the mean. As I told you, the confidence of SEM is very low, around 60%. So that is why the SEM is a lot more narrower than 95% CI. Student t-test, the first statistical test the students of the statistics typically learns, and hence the name? Of course not. The test was developed by W.S. Gossett, who are working with the Guinness Brewery in Dublin in Ireland then. To maintain the trade secrets of the brewery, Gossett had to publish the findings anonymously using a pseudonym student, and that is why the name student t-distribution came from. The t-test, to perform the t-test, we have to calculate the ratio, which is very simple. Mean of the sample 1 minus mean of the sample 2 divided by the standard error of the difference. In our earlier bladder example, so two group means subtract with each other divided by 6.67, which is our standard error of the difference in the group means. So you're going to get 3.53, which is our t ratio. The next step is to look up the t distribution table for the critical t value given a significance level and the degree of freedom. 15 is the degree of freedom because our data set has 16 elements, and the element, the significant level of the alpha is 0.05. The t critical, as we can see in this particular table, is that 2.131. So as the t critical, that is 2.131, is less than our t ratio, which is 3.53, we can conclude that the p-value must be less than 0.05. So the t distribution is derived from the the t table is from the t distribution through using the calculus. T distribution is an important probability distribution involved with a number of statistically significant tests. Earlier we have seen how this distribution is used for the calculation of the confidence interval of sample mean. T distribution is also used for the t-test as explained here, also for the linear regression analysis and Bayesian analysis discussed elsewhere. The table value is less than the calculated value, so p must be less than 0.05 and the difference is statistically significant. The exact p-value calculated by the software is 0.0030, which is indeed less than 0.05. In case the calculated t ratio is negative, no problem. Take the absolute value and infer the results. The sign indicates the direction of the difference. For example, had our calculated value been minus 3.53, results would have been still same, p-value should have been still less than 0.05 and the result is still significant. But remember the following points. Moser and Stevens in 1992 concluded that modified t-test that allows for unequal variances should never be used, as the results will be misleading. If F-test returns a low p-value which is significant or unequal variances, perhaps the best practice is to ignore the result and go ahead with t-test assuming equal variance. T-test is fairly robust to the violations of the assumption of the equal variances as long as the sample sizes are not tiny and the two groups have approximately equal sample size. That means you really don't need to do an F-test before a t-test. Simply perform the normal t-test and assume equal variances. Even t-test is not necessary. A 95% CI of the difference between the means would be enough to know whether the p-value is less than 0.05. If you do the t-test using the table method, still you are going to get only the p-value is less than 0.05. So it's not significantly different from our confidence interval based method. But if you're doing the t-test using a computer, you will know exact p-value, which is a lot more informative. There is yet another t-test which is called paired t-test, which is commonly used for before and after analysis or pairwise control versus the treated analysis, also for the matched groups. Assumptions for the paired t-test are random sample, accurate data, independent measurements for each pair from other such pairs. Differences between the matched values follow roughly Gaussian distribution. Remember, the values need not be the Gaussian, but we are looking only at the difference between the two group values, so that only the difference have to follow the Gaussian distribution. Also remember, for the paired t-test there is no assumption of homoscedasticity or the variances, so variances need not be equal for performing this particular t-test. Let us consider one example from the Darwin's 1876 results. He wanted to know whether self-fertilized or cross-fertilized seeds produce taller plants. He planted each pot with self-fertilized seed and cross-fertilized seed. By doing this, Darwin controlled for any changes in temperature, soil, light intensity and so on, as all would be same for each pot. As you can see in this particular table, cross-fertilized and self-fertilized and each of these paired values, the difference is given on the third column. So this entire table can be summarized in an excellent way by a before-after plot. Each value, you can see that most of the values are reducing in the self-fertilized comparing with the cross-fertilized, except two values which is actually increasing from the cross-fertilized to the self-fertilized. Given this table, let us first define our null hypothesis and alternate hypothesis. So our null hypothesis is that the mean difference between the paired observation is 0, while alternate hypothesis, the mean difference between the paired observation is not 0. So this is actually the difference between the paired observations differs or do not differ. That is exactly what it is. So how paired t-tests work? First, differences between each pair of the values are calculated, the third column in our table. Mean of these differences and 95% CI of this mean is calculated exactly as we would for the mean. So that is the t, the constant t from the t distribution multiplied by the standard error of the mean. That is exactly how we calculate the 95% CI of the mean. So the same way we can do that for this paired t-test. Mean difference, we found that in the table is 2.62 inches, while standard error of the mean is 1.22 inch. So we can calculate the 95% CI. So that extends between 0.003639 to 5.230. So as we can see here instantaneously, we can see that this range do not include our null hypothesis of no difference, that is 0. Of course, this range do not include the 0. So because the lowest value 0.0036 is still little bit higher than 0. So as 95% CI do not include 0, you can instantly conclude that the p-value must be less than 0.05. It's less but not significantly less. It's a little bit less than 0.05. So the width of CI depends on the variability, low standard deviation or low variance. That means the consistent data would lead to a narrower CI. Sample size large n would lead to a narrower CI. Degree of confidence or the confidence level, lower confidence would lead to a narrower CI. T ratio is calculated by the formula mean differences divided by the standard error of the mean of the two differences, exactly as in the unpaired t-test. So the mean difference here is 2.62 divided by the standard error of the mean, that is of the differences, that is 1.22. So 2.15 is our t ratio. Next step is to look up the t distribution table for the critical t value given a significance level and then the degree of freedom. As our n is 15, the degree of freedom is n minus 1, that is 14, and the significance level, of course, it is arbitrarily we use it as 0.05, and we can look up this value, that is 2.145, and the obtained value is 2.15. So the table value is little bit less than the obtained value, the calculated value of 2.15. So the p value must be less than 0.05, and the difference is statistically significant. But you should promptly infer that it's only a borderline significance because it is extremely nearer. The exact p value calculated by the software is 0.0497, which is indeed less than 0.05, and indeed it's a very pretty borderline. So this particular thing, if you are not doing, if you don't want to know the exact p value, then performing a t-test using the table is no more better than inferring the same conclusion by the confidence interval of the difference between the two group means. So the confidence interval approach is more intuitive, more easy to understand, and I suggest you to go for that confidence interval of the mean approach. So p value can be of two types, which is a two-tail p value and one-tail p value. Assuming null hypothesis of no difference is true, the probability of observing a difference as large or larger than the observed here is 0.0497. As this probability is low, we reject the null hypothesis. So now one-tail p value can be defined as assuming null hypothesis of no difference is true, probability of observing a difference as large or larger than what we observed here with the cross-fertilized seal. Self-fertilized plants growing more than the cross-fertilized plant is 0.0248. The other way around is also, that is with cross-fertilized plants growing more than self-fertilized plant is also 0.0248, which are the one-tail p value. The double mostly is our two-tail p value, and as I explained earlier, it's always preferable to go with two-tail p value rather than the one-tail p value. So the p value depends upon the p value will be smaller if the mean difference is much greater than 0. So the two group means are not much different, so the p value will be smaller. So the p value will be higher if the mean difference between the two group means will be higher, so or the effect size. So p value depends upon the effect size. So p value also depends upon the consistency of the data, that is the standard deviation or the variance. A low standard deviation, p value will be smaller. A large sample size would lead to a small p value. So of course the sample size is a big determinant for the p value, so you can increase a lot the sample size by many-fold, and the effect size need not be high for getting that exactly same p value. So in summary, the t distribution is a very important probabilistic distribution that we can use it for a number of significance tests, especially for the t-test, which is used to compare the means of two groups, group A and group B. So to compare the means of these two, either dependent group or independent group, we can use a t-test. We can also use a t distribution for a number of other statistical operations, for example the confidence interval of mean. So instead of performing the t-test, we can also do the same thing by looking at the confidence interval of the difference between the two group means. So I've explained to you in this module how to calculate the difference between the two group means. So instead of performing the t-test, we can infer the same conclusion. Is it statistical difference, or is it the significance of the statistical significance of the difference? We can infer the same thing by looking at the confidence interval of the difference between the two sample mean. In addition, the t distribution is also used for other tests, like for example the linear regression as well as Bayesian statistics, that we will actually come up in our the next module. Thank you.